Okay, good afternoon, everyone. We're very happy today in the GTP seminar to have Theo Johnson-Freyd from Perimeter and Housie, who's going to tell us about higher Dagger categories. Theo, please.
Okay. Well, thank you very much for the invitation to present to you. It's very exciting. I want to tell you about a project that I did with a very, very large number of people, and I'll say a moment by how you end up with a project with 12 co-authors. So my co-authors are Bruce Bartlett, Gio Ferrer, Brett Hunger, Cameron Kurliski, Lucas Mueller, who I think is here on the zoomed in, Nivedita, Dave Pennies, David Reuter, Claudia Scheinbauer, Luke Stehauer, and Chetan Vilpaluri. Okay, and also these slides you can download if you want to read them at a different pace than I'm going through them. I think I'm sure we are going to get this paper on the archive this calendar year. I almost wrote 2311.allx's because I think there's a good chance we get it out this month, but I sort of didn't want to commit myself to that because I don't know, the last time I spoke was 2310 and I had written that. So, okay, so yeah, so let me tell you about higher Dagger categories and what we've done with them. So let me give some background. So back in maybe 2007, roughly, Peter Selinger supplied the following definition. The versions of this notion had been around, but Selinger really kind of gave the term and gave the axiomization. Selinger says that a Dagger category is a category, just an ordinary category, one category, together with an extra piece of data, which is an assignment for every morphism from X to Y, another morphism from Y to X, called its Dagger. And there were two axioms. The first axiom was that Dagger squareds the identity. And the second axiom is that Dagger is a contravariant functor. And the kind of prototypical example, the example that you are always supposed to keep in mind is the category of Hilbert spaces, and where Dagger is the adjoint of the bounded operator. So Hilbert spaces in bounded maps and the adjoint operation. There's lots of other examples. For instance, you could take the sort of versions of Hilbert spaces that you can vary. You could vary the field of definition for Hilbert spaces. You could work with sort of indefinite Hilbert spaces, inner product spaces, Hermitian spaces. You could turn on a group. It's really interesting. It's useful to have Dagger categories around to be able to organize unitary representation theory of, say, a locally compact group. Another collection of motivating examples that people really do care about are categories of relations or spans or correspondences, whatever you want to call them. And I think another set of examples that someone like Selinger would really want to work with are categories of diagrams, maybe categories of graphs and kind of, so not correspondences, but I think it's respondences, co-correspondences. So that's a bunch of sort of standard examples. And from the beginning, you can go onto the kind of archives of the NLab and find discussions from early on about how this definition seems evil. Where evil means that it's not quite coherent, that a Dagger structure, this is not an example of a category with a structure. Well, it is an example of a category with a structure in the strict case, in the sense of if you work with the strict one category of categories. But normally you think that if I want to say, what is a group? A group is a set with some extra structure on it. And if you have two isomorphic sets, you can transport that structure across the set. And so it's something, whatever a group is, it's something you can define in terms of the category of sets. And it doesn't really care whether set means set in the way that Zermelo and Frankel define set, or set in the way that Bourbaki defines set. A group is still a set with some structures. A Dagger category is that for the strict one category of categories, but the strict one category of categories is not what we mean when we talk about categories. We mean the infinity one category, the 2-1 category. We mean that when we talk about categories, we want to consider equivalent categories as the same. And the problem with Dagger structures is that if you have an equivalence of categories and a Dagger structure on one of the two categories, you cannot necessarily transport it across to a Dagger structure on the other one. As I said, this has been a known feature or problem with the definition since the beginning. And the received answer, the answer that had been established maybe 15 years ago, I call it Selinger's answer because, as I said, you can go on to the NLab kind of archives and find this discussion. People like Selinger were saying, look, Dagger categories are just a different thing. They're just not supposed to be categories with a structure. Category itself is already an evil notion because when you talk about composition, the composition was something like hom xy times hom yz to hom yz. This also requires referencing objects exactly. You said that this object is equal to this object. And the problem with the Dagger category is it references objects exactly. It doesn't reference objects up to isomorphism. It says that this map, that Dagger of something from hom xy goes exactly from y to x, and not from something isomorphic to y to something isomorphic to x. So the standard answer was Dagger structure categories are just a different thing. They're not categories with structure. They're a different type of beast. And this is fine. There's a perfectly good Dagger category theory. There's a perfectly good notion of Dagger category and Dagger functor. And it's natural in the world of Dagger categories and Dagger functors not to use arbitrary natural isomorphisms, but to use unitary natural isomorphisms. Dagger categories, one of the features of Dagger categories is that they have two different types of isomorphism in the Dagger category. There's categorical isomorphism and there's unitary isomorphism. And these might be different notions. As you know, the group of automorphisms of a vector space is not the same as the group of unitary automorphisms of that vector space if you pick a Hilbert structure. So that's just a feature of the theory. So this would all be well and good, and I would be satisfied if I were satisfied with just ordinary one categories and a kind of set theoretic mindset on one categories. And but I'm not, because I want to do higher quantum field theory, and I think a lot of people in this audience want to do quantum field theory in high dimensions, and I want to do higher category theory. And ultimately, we want to do sort of some type of higher functional analysis, some sort of theory of higher Hilbert spaces. And these will not form a strict N category. At best, they'll form some sort of infinity N category. And our best model, our best picture of infinity N categories doesn't have sets built in at all. It's really built in a kind of world of homotopy theory or space or topological spaces. And so we need a version of Dagger theory, of Dagger category theory, that doesn't reference the sets of objects, that never asks that objects be equal. So that's the kind of question. And last spring, I started hearing, this wasn't a question that I planned to engage with. I just planned to sit back and wait for somebody else to figure it out. But last spring, I started to hear a couple different groups of kind of friends of mine and their collaborators who seem to be approaching this same question of what is a Dagger N category. And they were starting to tell me things. Nobody had a complete definition yet. But I started hearing bits and pieces of things that had some overlaps and some things that I was worried might end up being in conflict. And I thought, what a disaster it would be if around the same time, two different groups of people released papers proposing definitions that were competing. Like that would be horrible. So what I did with Lucas, who's here in the audience, and with Dave Pennies and a few others, and then a slightly larger group, was we organized a small Zoom workshop in June. And basically to get together and talk it, sort of work it out, finish the question of what is the definition of higher Dagger category. And it was a really fun workshop. We had maybe 16 people. People gave talks with their bits of the definition. People talked about various examples that they wanted to be examples of higher Dagger categories. And then we had lots of time for discussion. And at the end of the week, we kind of came out, for the 16 of us, with a definition we all agreed was the right definition of Dagger higher category. And we sort of, everybody contributed to the conversation. Not everybody wanted to be an author on the paper for whatever reason, but that's how I ended up with a paper that has, what, 12 or 13 authors on it. Because that 12 or 13, well, 16 people contributed, and a few people decided that for what their own reasons didn't want their name on the paper. Basically because they didn't want to kind of, there's like, you contribute to a paper, but then you also have to actually like keep being involved with the writing, and writing takes a lot longer than sitting around in a workshop and talking. So the only reason that a few people bowed out was they just didn't have the time to be engaged with the writing itself. So anyway, so now that's my goal, is I want to tell you what we figured out in this series of these conversations we had. So let me go back to the one-dimensional case first. I'm not going to yet try to tell you what a Dagger N category is. Let me try to tell you what a Dagger 1 category is, but in a coherent and a less evil way. So remember that what a Dagger category was, is it had a functor called the Dagger, and this was a functor from the category to its opposite. And this functor was an involution up to this taking opposite. So it was an anti-involution. So it was a Z2 action, a Z2 fixed point. And that's a perfectly non-evil notion. It's perfectly coherent to talk about having a Z2 equivariant isomorphism, equivalence between your category and its opposite. So I'm going to call this, so let me say it sort of for a third time. The category of all categories, the infinity one category of all one categories, has an involution. It has a Z2 action, which takes C to its opposite. And if you have a Z2 action on a category, you can ask for the fixed points of that Z2 action. If the Z2 action is trivial, then the fixed points are called representations of Z2, but if otherwise it's just the fixed points. And I mean this in the homotopical sense, in the categorical fixed points, the coherent fixed points. So I'm going to say that a fixed point for the Z2 action, for this Z2 action on categories, I'll call that a whippage category. Whippage was a term we decided we needed a word, and we went and asked ChatGPT. And ChatGPT knows a lot of English, and if you ask it good questions, it gives you decent answers. So ChatGPT told us that whippage stood for work in progress edge, and it made up that term. So it's on its way to being a Dagger. It's not quite there yet. Okay, so that's part of the definition, but that's not the complete definition. If you think about the category of Hilbert spaces, you could start with the category of, let's just forget about infinite dimensions for now, because there's a way to say what I'm going to say in infinite dimensions. You have to sort of say all the right words in Banach theory. Let's just talk about finite dimensional vector spaces for a moment. The category of finite dimensional vector spaces over the complex numbers has a whippage structure that sends a vector space to its star dual. So this, so you take its linear dual. Yeah, what do I mean? You take its linear dual, and you take its complex conjugate. And of course, taking complex conjugate as a covariant operation, but taking linear dual as a conjugate operation. And so this assignment of a vector space to its conjugate dual is a fixed point for the functor that's for the C goes to C op action. And that's part, if you want to figure out what is a Hilbert space, part of being a Hilbert space is something about V mapping to V conjugate opposite. It's something about a relationship there. But there's more to being a Hilbert space than just saying that your vector space is symmetrically isomorphic to its conjugate opposite. Because this much isn't able to tell the difference between, say, Hilbert spaces and Hermitian spaces. To tell that extra difference, I need to trivialize, I need to put in this other piece of axiom in a Dagger category that said that the Dagger on objects was the identity. And now you have to think very carefully about what it meant when you said the Dagger functor, when restricted to the set of objects, is the identity. the dagger of an object is that object itself on the nose and not something just abstractly isomorphic to it. This is, of course, not true, actually. It's not really true that the dagger functor restricts to the identity on the space of objects. It restricts to the identity in the Selinger definition. It restricts to the identity on the set of objects. And what's evil in the Selinger definition is talking about the set of objects. Categories shouldn't have a set of objects. Categories should have a groupoid, a homotopy 1 type of objects. And if you take the dagger function and restrict it to the homotopy 1 type of objects, it's not the identity in the category of Hilbert spaces, for instance, because not every isomorphism is a unitary isomorphism. In a dagger category, there's another groupoid. As I said, there's 2 types of isomorphism in a dagger category. There's the categorical isomorphism, so the linear isomorphisms between Hilbert spaces, and there's the unitary isomorphisms. And a dagger category has this as extra information. That's what remembering the groupoid of objects up to unitaries is what remembers the difference between Hilbert spaces and Hermitian spaces. So let's build that into the definition. So the definition, which was, I think, separately given by Simon Henry and by Lutz Stiehauer and Jan Steinebrunner, or they didn't say it exactly the same way, and they didn't use this word whippage, but they gave essentially the same definition, is that a coherent dagger 1 category or a coherent infinity 1 dagger infinity 1 category is a whippage category. So one of these anti-involutive ones, a category with a fixed point structure for taking the opposite category. Together with another groupoid, that's just a groupoid or infinity groupoid, which I will think of as the object's mod unitaries. And that groupoid lives inside of the category. And there's 2 axioms that make this work out. One of the axioms is the following. First of all, I want you to think in the example, think of the example where C1 is say finite dimensional vector spaces over the complex numbers, where the whippage structure is mapping a vector space to its conjugate dual. Then the Z2 fixed points among the objects for this action of a vector space to its conjugate dual, these are the Hermitian vector spaces. I want to take the groupoid to be the Hilbert, the positive definite vector spaces. And the axioms that I put in are the following. First, not every Hilbert space, not every Hermitian space is a Hilbert space, but an isomorphism, like to be a unitary map, I don't need to know whether I'm Hilbert or not. So the inclusion of Hilbert spaces among Hermitian spaces should be a fully faithful map. It's a union of components. So that's one of the axioms, that this arrow should be a fully faithful map. The other axiom is that the map from the groupoid of Hilbert spaces to the category of vector spaces is essentially surjective. In other words, I'm demanding that every object of my category does admit at least one Hilbert structure for my dagger structure. And that's a totally reasonable axiom, because if there were vector spaces that didn't admit Hilbert structure, fine, I just wouldn't keep them around when I was talking about the category of Hilbert spaces. I'm trying to capture the category of Hilbert spaces at the end. Okay. So that's my definition. I realize I've been talking fast and maybe there's questions, and please interrupt at any moment. And I see a hand, but I also can barely see on the little Zoom screen. So
yeah, can I ask a question here?
Yes, please.
I'm sorry, could you just be more explicit about how precisely this reduces the Hilbert spaces and Hermitian spaces in the very traditional setup?
Yeah. So let me do that. That's great. I will explain that in much more detail. Let me to motivate this, let me state the next thing I was going to say, okay, which is a strictification theorem. I call this the Stiehauer-Steinebrunner strictification, and I find it hard to say that trio of words. So Stiehauer and Steinebrunner proved that this definition, when done on just strict 1 categories, but with the 1 categories, coherent dagger 1 categories, is equivalent to the traditional 1 categories. And maybe I think what I should do is I should tell you what this equivalence is. So let me Let me just do that in detail. And then I'll sort of dive into the n-dimensional version of my story. So let me tell you about this how Stehauer-Steiner-Brunner strictification works. And I'll just do the example of Hilbert spaces. So their motivating example is the following, and everything I'm saying right now is just from their paper. It's not new to this work, but their example is the following. So they say, let's take the category of finite dimensional vector spaces, or reflexive topological vector spaces, if you want, for what I'm going to say. And let's give this, first of all, I want to give it what I'm calling a whippage structure. So what I want to do is I want to give it fixed point data so this is my category. This is an object of cat. And I want to make it a fixed point for the Z2 action that takes the category to its opposite. So my Z2 action takes it to, of course, the opposite category. And the whippage structure would be an equivalence, would be a functorial isomorphism, an equivalence of categories between vec and its opposite. The whippage structure is, I'll take the following equivalence of categories. I'll take the equivalence of categories that takes an object to its conjugate dual and a morphism to its conjugate dual. So as I said, that's a contravariant functor because I took duals. And it's a Z2, it's a fixed point for the Z2 action because indeed the conjugate dual of the conjugate dual is naturally isomorphic to original vector space. It's not equal to your original vector space, but I'm doing it coherently. It's naturally isomorphic. Okay. So this will be my example. I'm calling that C1. And then now you can work out what is a fixed point. What did I call it? I called it, so Iota 0 C1 is my notation for the objects, for vector spaces up to isomorphism. So the groupoid of vector spaces up to isomorphism. And you can take the fixed points under this whippage structure. So you can ask for a vector space up to isomorphism, which is Z2 fixed under, which has a symmetric equivalent. So this is now the groupoid of V with a symmetric isomorphism to its conjugate dual, or in other words, a symmetric sesquilinear non-degenerate form. So this is the groupoid of Hermitian vector spaces. And then I pick, as I said, I pick C0 to be the subgroupoid. This is my choice, subgroupoid of positive definite ones. That was my choice. Okay, now I want to give you a strict category back. So this was, I told you that I had a strictification. I need to give you a strict Dagger category back. So what I can do is the following. I have a map to get a strict Dagger category, a sort of Selinger style Dagger category. What I do is the following. As I said, I had this groupoid of Hilbert spaces and unitary isos. That was my groupoid. This was my C0. I have a map from here, an essentially surjective map. Doesn't matter that it's essentially surjective, but I have an essentially surjective map to the category of vector spaces and all linear maps. And now what I can do is I can take the full subcategory on these objects. So I can build a new category with the objects being the objects of C0. but the morphisms are the morphisms of C1. So an object is an object of this groupoid, and given two objects of this groupoid, I just declare the morphisms to be the morphisms between their images in this category, the morphisms of underlying vector spaces. This is, of course, what the category of Hilbert spaces is, if you don't remember the Dagger structure. Because this is essentially surjective, this category is just equivalent to C1 by the essential surjectivity. It's not necessarily equal to C1 because a given vector space has many Hilbert structures on it. So it's just equivalent. It's equivalent to C1. So this is my new category that's equivalent to C1, but it's not equal to C1. And now I claim that this new category is a Dagger category in the strict sense, in the traditional sense. And so this new category is a Dagger category in the Salinger sense. And maybe I let you work out that very last step. But in this case, it just is the category that you think the category of Hilbert spaces should be. The category of Hilbert spaces should have its objects the Hilbert spaces. Indeed, my new category has its objects the Hilbert spaces. And the linear maps are the linear maps that the Dagger structure knows about the adjunction data. So the Dagger structure uses the fact that
Sorry, can I ask a naive question?
Yeah.
So in this construction, didn't you want to make the double dual of a Hilbert space to be equal to that Hilbert space? Is that?
That's right. So what I'm saying, so this is what
How does it happen here?
So C0 was a full subcategory of the fixed points. And so that just gives you the identification between, that sort of is what trivializes the Dagger structure. So I didn't require that, yeah, so what did I really need to do? I didn't need the Dagger structure to be the double dual on the category of Hilbert spaces. Of course, the Dagger structure is not the double dual on the category of Hilbert spaces, it's some formula. But I'm claiming more generally, here's the more general claim. The more general claim is that if I have two, here's the point. The point is that if you have two objects which are fixed under the involution, under the Whippage structure, and a morphism between them, then using that fixed point data, you can give a Dagger to that morphism. So what I have is I have an object and a chosen isomorphism to its double dual, to its star dual. I have another object and its chosen, and together with its chosen isomorphism to its double dual. And if I have any linear map between these two objects, so these are just Hermitian objects, possibly Hilbert objects. But a priori, this is something that would work for any Hermitian object. If I have an object with an isomorphism to its double dual and an object with its isomorphism to its double dual, and any linear map between them, well, I get its corresponding conjugate dual linear map in the other way, just because conjugate dual is a functor. It didn't matter what it was, it just needs the conjugate dual as a functor. But now this composition will be my definition of the star of F Dagger. So what I'm really saying is actually that there's a sort of, if you take any Whippage category and take the fixed points for the Whippage structure, that's naturally a Dagger category. In this case, that's the Dagger category of Hermitian vector spaces. And now I'm allowed to reach inside of it and find a full sub-Dagger category. In this case, the full sub-category Dagger category of Hilbert spaces.
So just to be clear, there's nothing in the Dagger structure per se that says positivity. It's this extra feature. There's always this sort of maximal strict Dagger category you can extract from the Whippage structure. but you could
That's
also
exactly right.
other ones, and in this case, you can add in positivity.
That's exactly right.
Thank you.
Yeah, just to repeat what you said, any whippage structure has a maximal dagger category that it determines. There's some adjunction between whippage categories and dagger categories that gives this. And there are other dagger categories for the same whippage category that impose extra positivity conditions is how you should think about those other ones. And they are different as dagger categories. The dagger category of Hilbert spaces is different from the dagger category of Hermitian spaces. There's a dagger functor from Hilbert spaces to Hermitian spaces, and there's no dagger functor in the other direction. But like the dagger functor from Hilbert spaces to Hermitian spaces is an equivalence of categories, but it's not an equivalence of dagger categories. It has an inverse, but that inverse functor is not a dagger functor. Okay, so that was our definition, right? And I can tell I'm going slower than I had hoped, but maybe I'm almost halfway through my slide. So now I'll just repeat the definition, but where every one becomes an n. So let me tell you the definition, our definition of dagger n category. So let me write cat infinity n for the infinity 1 category of infinity n categories. It's some nice presentable infinity 1 category that's fairly well understood by now in the literature. And let me point out that the definition of dagger category, the definition of whippage category, used the fact that I had this canonical Z2 action on cat 1, namely sending a category to its opposite. And actually, that is every involution. The category of 1 categories has exactly a Z2 symmetry. And more generally, Clark Barwick and Chris Schomer-Priest in their beautiful unicity paper prove that if you take the category of n categories and calculate its automorphism group, you get precisely the obvious automorphism. So the obvious automorphisms are just to take the opposite category in any of the n dimensions of composition. And what they prove is that there's nothing else. But that's exactly the automorphism group of the category of n categories. And so it makes it completely natural to talk about a whippage n category to be a fixed point for this action. And I should have said this much earlier. Okay, I don't know why I put on this slide and not 5 slides earlier. Let me just keep pounding home. Of course, when I say fixed point, that's data. It's a whippage structure. And more generally, you could sort of, I'll leave that, maybe I leave that out. You can do more general things where you take subgroups of Z2 to the end, but the interesting thing for me is the full automorphism group. So as in the one-dimensional case, just being a fixed point for all the different involutions is not enough to say you have a dagger category. Of course, there will be a maximal dagger category for that whippage category, but in examples, we want to remember further positivity type information, further information that we think of as positivity. So just for some notation, I'll write, I forget why we decided to call this Yoda, that throws away the top few morphisms. So if I have an n category, I can throw away some non-invertible morphisms and get the maximal sub n-1 category, n-2 category. So for instance, the maximal subgroup weight of a category. And you can work out the following. If you take an n category with, you can work this out just by like tracking through how the different actions work. If you take an n category, which is fixed under the full Z2 to the n, and if you restrict the top some set of like the morphisms above m to be invertible, then it still has fixed point data for all the morphisms, for all the taking opposites below dimension n, below dimension m. Okay, I should not have used m, I should have used k, because I can't say the difference between m and k very well. Okay, if you take an n category and restrict it to being a k category, you throw away the things in dimension above k. The k category had a sort of z2 to the n. If it was whippage, that was a z2 to the n equivariance. And this operation of throwing away top morphisms is compatible with that equivariance. It keeps around an n minus k many equivariances for the n minus, it keeps around a k many. So this was like a Z2 to the N thing. You throw away some things and you get a Z2, you still have Z2 to the K equivariance for that's actually taking opposites of the K directions that you have that are non-invertible. But an invertible map, like, has a canonical way that it's equal to, that, what am I saying? Every invertible map, you already know a canonical way to turn an invertible map around. You take its inverse. So using that, you can untwist Dagger structures on groupoids, is what I'm saying. And so when you untwist it, you still do get, you have a residual n minus k many Z2s that's just an action. And so our definition is that an n category, a Dagger n category, is a sequence of a 0 category, a 1 category, up to an n category, where for every k, I really should have written this with k so that I don't. For each k, if you take your k category, restrict it to being a k, if you take your k plus 1 category, restrict it to a k category, and look at the Z2 fixed points of that, you have some subcategory of that, which you think of as the positive ones. So when k was 0, this is the definition I gave before. And then I still have this sort of essentially surjective and fully faithfulness axioms from before. Let's see where they were. Versions of these two axioms. So the map from, so this map without, so the map into the fixed points is fully faithful on high enough morphisms. And the map into without the fixed points is essentially surjective on low enough on morphisms below some cutoff. And this turns out to be what we believe this is the right definition. I should say in this whole project, we have not done a lot of examples. So all of this is like, we're pretty sure this is the right definition, but I will be more sure when more examples come along.
Can I ask you,
so,
sorry.
Yes,
Can I
please.
ask one question on this? So you have no condition on the sequence of the CMs that they somehow embed into each other in some way, or is this implied?
Let me, well, let me repeat the definition, but say what's implied.
Right.
So what's implied is that actually, so I told you something about like each CK mapping into the next one. I just sort of told you about these consecutive maps and these triangles. But from this, you can just get a big triangle just from unpacking kind of who's fixed inside of whom and how the equivariance works. And what you find is that for any triangles, you know, any sort of, at least any triangle, that any sort of subtriangle along the top row, so any CK into CL, you get an interesting map from CK to CL, which factors through some fixed points. And this interesting map from CK to CL ends up being essentially surjective up to dimension K. And the factorization through the fixed points ends up being fully faithful starting in dimension L. And so this is an equivalent way of axiomatizing it. And this picture that has all possible pairs of K and L is actually the better picture. It's the one that works better if you want to work with kind of G Dagger structures for other subgroups, for other groups that aren't the full Dagger structure. Did that answer the question?
Yes, thanks.
Okay, so the reason I drew this big thing and expanded it out was for the following. So this is all well and good, but it's not the end of the story. Because as I said, my goal from the outset was to talk about quantum field theory. Well, quantum field theory is too hard for me. Let me talk about topological quantum field theory because I understand that better. Topological quantum field theory is very much about the theory of adjoints and duality. So sort of adjoint functors, dual vector spaces, that kind of stuff. So let me remind that an N category is said to have adjoints when every K morphism has both a left adjoint and a right adjoint in the dimensions where that's meaningful. So 0, sort of K strictly between 0 and N. And I'll just write adjcat for the full subcategory of cat N on those objects with adjoints. So the cobordism hypothesis, there's something called the kind of cobordism hypothesis with singularities, which is kind of very briefly sketched at the end of Lurie's paper on CFTs. It has not been fully worked out. But it is a statement that says that the graphical calculus that everyone knows and loves in low dimensions, some version of it should also be true in high dimensions. That's the kind of the slogan version of cobordism hypothesis with singularities. And it makes it a little bit more precise. The statement of cobordism hypothesis with singularities tells you what types of framings to put on the string diagrams. And now you could scratch your head and wonder, do I want smooth diagrams or piecewise linear diagrams? Like junctions are just not smooth at all. They're very definitely piecewise linear. You can ask yourself, which do you want? And the answer is you don't care. There's a magical thing called smoothing theory, which tells you that if you have enough framings around, then there's no homotopical difference between smooth and piecewise linear manifolds. And piecewise linear manifolds are really the natural thing for drawing pictures of morphisms of composition. So let me write PLN for the piecewise linear automorphisms of Rn. And if you take this, if by diagram, if your higher dimensional string diagrams, if your graphical calculus was by definition about piecewise linear diagrams, then the group PLN acts on the space of all piecewise linear diagrams. And the statement of there being a graphical calculus, what does that statement mean? It tells you that you're supposed to think of an n category with adjoints. The definition of n category with adjoints should be that an n category with adjoints is some sort of interpreter for these diagrams. That's not the definition. I gave a definition of n category with adjoints, but the statement is that another definition is that an n category with adjoints is an interpreter for diagrams. But if diagrams have an action by PLN, then dually the space of interpreters for diagrams has to have an action by PLN. And so you should expect, this is not proven except for in very low dimension, but what you should expect is that PLN acts on the category of n categories with adjoints by rotating the diagrams. You can do the same thing this has been spelled out a little bit better in Lurie's paper on the cobordism hypothesis. So you can do the same sort of smoothing theory arguments and say, well, the category of smooth framed bordisms, the symmetric monoidal, this is the sort of symmetric monoidal automorphisms. Whatever the n category of smooth framed bordisms is, even if you didn't know the cobordism hypothesis, you would still know that PLN acts on this category by rotating the frames. Because that's what smoothing theory tells you. It tells you that smooth framed bordisms are the same as piecewise linear framed bordisms. Up to a contractible space of choices. They're the same up to a contractible space. They're the same for an infinity category. And so you get an action by PLN on board N. And then there's I'll call it a theorem of Lurie's. Lurie asserts this without proof in his cobordism hypothesis paper. He has communicated the proof privately to a few people who have then gone on to communicate the proof privately to a few other people. I'm not on the list of people that has received the complete proof of this statement. So I don't know, but the statement is, if you believe the cobordism hypothesis, then this action by PLN to board N is an iso, or it's an equivalence of higher groups. It's an iso of homotopical groups. Well, it's an iso except for in dimension 4 where it's an open conjecture. Maybe it's an iso in dimension 4 as well, but there's some open conjecture in topology that's equivalent. So let me make a bold conjecture. My bold conjecture is that this type of statement is true for not symmetric monoidal, not the bordism category, but for the category of categories with attributes. And again, you should be suspicious, especially in dimension 4, where all topology breaks. But as I said, we don't even know that there's a map like this. It's not proven that there's even a map. And I'm conjecturing that the map that doesn't necessarily exist is an iso. So let's take that conjecture for fun faith. And if you assume this conjecture, then then it makes sense to repeat my definition of Dagger category, but for categories with adjoints. My definition of Dagger category started with a whippage structure, a fixed point for the full automorphism group. Now my full automorphism group is PLN. So I can ask for fixed points for the full PLN action. I'll call this a whippage category with unitary adjoints. I'll come back in just a moment to explaining why I call them unitary adjoints. And then I can repeat the definition for Dagger structure. Before, what I did when I talked about a Dagger category was I took like this, diagram of sort of whippage objects, and I said I should have an arrow that factored through some fixed points. And the fixed points were like, this is an arrow of whippage K categories, and this, remember, was a Z2 to the L minus K, because I could take Z2 to the K and factor to Z2 to the L, which was kind of what's going on here, and Z2 to the L minus K. Well, the piecewise linear group doesn't factor as a product, but it has a product living inside of it. And so I'll just restrict the action and do that factorization. And so this will be my definition of Dagger category. Dagger category with unitary adjoints is just like on this page. It's a big diagram where each C on the top row is whippage, where you have a bunch of kind of maps of whippage categories into fixed points of the next things, with some essentially surjective and fully faithfulness axioms. So this is our proposed definition. So you can work this definition out very explicitly in dimension 2. In dimension 1, there's no notion of adjoints. A one category can't have, like a one category just sort of has adjoints trivially because there's not enough room to talk about adjoints. But if you look in dimension 2, the group PL2 is homotopy equivalent to the group O2. Deformation retracts onto O2. O2 has just two pieces. It has a reflection and it has a rotation. And on infinity 2 categories, there's some higher coherence that I'm not going to talk about. But for bi-categories, the reflection you can think of as just taking a category to say it's two opposite. You can just take the opposite of the two morphisms. And the rotation takes a category. Well, this is a BZ action, so it's a thing that takes a category to a natural automorphism of that category, rather than a category to another category. It takes a category to the natural automorphism called double right adjoint. That's a natural automorphism of any bi-category with adjoints. And if you work out what a Dagger category with unitary adjoints is in this case, what you find is it's a bi-category with adjoints, where the top dimension, the sort of one category, the sort of top part are all Dagger categories. So every top morphism has a Dagger. That's part of the data. That's like the Dagger structure for this Z2. And the Dagger structure for this BZ ends up actually unpacking to a pivotal structure. Trivial is like it says that every morphism should be identified with its double rate dual. And also there's a compatibility that the evaluation and co-evaluation maps should be unitary. So that's what it ends up unpacking to. That's why we think of this as like examples of categories of unitary adjoints. It's this very funny thing that people have kind of observed a few times, which is that, of course, if you have a morphism and if it admits an adjoint, then the space of adjoints is contractible. I mean, the space of pairs of an adjoint and an evaluation map and a co-evaluation map witnessing it as an adjoint. That's a contractible space for every morphism. But if you have a morphism and you ask for it to have a unitary adjoint, then there's data in the unitary adjoint. Because not every evaluation and co-evaluation pairing are going to be unitaries. I said this wrong. Evaluation and co-evaluation are not unitaries. What is the actual statement? This is totally wrong. I wrote these slides, what was early this morning. Okay, and the statement is that something like that F Dagger is co-ev of F dual, something like that. That's the statement I should have said. So this is this does not necessarily hold for just some random choice of adjoint for your functor. It's an extra axiom which breaks your contractible space of adjoints to a non-contractible space. And being a PL dagger category, being a dagger category of adjoints in the sense that I told you, is making these choices. Sorry, and this is why it makes it pivotal, because now if you apply this twice, while daggering is an involution, I mean, this doesn't even parse. This is kind of, okay, I forget what the exact formula is. Maybe Lucas is in the audience and can tell me. So that's the first example that we had. I have -2 minutes left, or I have 8 minutes left. I wasn't quite sure, so I will end in less than 8 minutes. Let me give 2 more examples and then just to sort of announce them, and I can explain them in great detail later, but maybe I should do it after I finish the formal talk. So my motivation from the get-go was to do quantum field theory, to do topological quantum field theory. I think a lot of people in this audience know about this stuff. The way topological quantum field theory tends to work is people like to write down Bordism categories, where you take a category, an N category, a symmetric mental N category of Bordisms with H structure. Maybe you have an oriented Bordism category, or a spin Bordism category, or a Bordism category with a G bundle, or whatever it is. You can have piecewise linear Bordism categories, smooth Bordism categories, and all of that. So all of these are given by tangential structures. If you have a piecewise linear manifold, then it has a tangent bundle, which is classified by a map to BPLN. A tangential structure is a lift of the tangent bundle through some other space. That's the definition of tangential structure, and this is the input to talking about a Bordism category. So an H-structured manifold is a manifold equipped with such a lift. I mentioned smoothing theory already. It's a sort of magic, quite deep statement of differential topology that smoothness itself is a tangential structure up to a contractible space of choices. Let me say that a tangential structure is stable. So a tangential structure is something that depends on n dimensions. I'll say it's stable if it kind of comes from something infinite dimensional. This is extra data. The same tangential structure might have more than one stabilization. It might have no stabilizations. Smoothness itself is not quite stable, but it's very, very close to being stable. And our theorem, which I'd be happy to explain in private, is that if you have a Bordism category with a stable tangential structure, then it's naturally Dagger, in the sense that we said. And maybe the last example I want to announce, this is not my example, this is a work of, so Gio and Brett and Dave are co-authors on this project, and they also had 2 other co-authors on the other project that I'm mentioning. They, in some other work, have a notion of n-dimensional of n Hilbert space, n categorical Hilbert space. Well, at least they have a finite dimensional n Hilbert spaces. And their work is kind of checked up to dimension 3. So in dimension 2, it was already basically like it recovers known things. Topology is hard in dimension 4, but in dimension 3 is where they really have some new result, some new rigorous result, and they have a sketch in higher dimensions than that. And their statement, as I said, rigorous in dimension 3, is that their category of Hilbert spaces, their 3 category of 3 Hilbert spaces is Dagger in the sense that I told you. They can also do a kind of superversion of this, and so this actually means we can talk about what a unitary fully extended quantum field theory is. So I propose that a unitary field theory should be a functor. Well, fully extended field theory was a functor from board n to n vec, to the n category of vector spaces, and I propose that a unitary thing should be a Dagger functor compatible with adjoints from board n to their n held. So I think I should stop here. Thank you for your attention.
Thank you. Any further questions for Theo?
Yeah, so in your definition of Dagger infinity n category, when you like do the big triangle,
yeah,
then like the top the top row is exactly the same datum as a flagged infinity M category, i.e. an n-fold, not necessarily complete Siegel space?
Yes, this is exactly correct. And this is the way we figured this out. I sort of decided in this talk not to say the word flag just because I had finite amount of time. But yes, absolutely, you're exactly correct. And if you dropped this fully faithfulness axiom but kept this essential surjectivity, this is what we would call a flagged Dagger category.
Right.
As you said, the top row is literally a flagged category.
So are you able to express the whole thing as just like some sort of nice, maybe like n-fold symmetrical diagram together with like some more factors or something? So it's just like becomes some sort of nice diagram of spaces. You know what I'm trying to say?
I have a sense of what you're trying to say. I don't know the answer to it. It's a great question. We certainly didn't investigate this type of thing. Our goal was and remains kind of do a short paper that just gets a definition out and then go tell everybody it so that you can figure that type of thing out. Yeah, no, definitely this is certainly an example of a flagged category with some extra stuff. So the way I would think about it is that this row is a flagging, that this essential surjectivity is the axiom in kind of for flagged categories.
Right.
And if you ask, like, when is a flagged category just a category? Well, a flagged category is just a category when not only is this essentially surjective, but also has a fully faithfulness type axiom.
Right.
And that's a sort of univalence axiom. And so I think of this as being the flagged stuff, and this is the univalence axiom.
Right.
And the difference is that in Dagger categories, the essential surjectivity and the univalence are imposed on different maps.
Hmm. Okay.
Very good. Any other questions? Last one question.
Yeah, thanks for the nice talk. I'm wondering about what happens if you impose unoriented structure and self-duality in your definition. So let me explain what I mean. If there's kind of a little issue that people tend to gloss over in just the ordinary formulation of these topological field theories, but where you for instance, say, okay, let's do topological quantum mechanics, say, as a factor from board one to say complex vector spaces in some naive setup. And then if you ask what happens if one imposes now the condition that the one-dimensional cobalt is actually unoriented, say we're looking at self, then the condition becomes, or the cobalt is not, or whatever, then the condition becomes that we're assigning to the point a self-dual object in complex vector spaces. That's actually a funny thing, because that is a finite dimensional complex vector space equipped with a bilinear form.
That's right.
Which is something quite alien to, it's not something you want to see in quantum physics. You want to see a Hermitian form, right?
Yeah, so I would respond to this in a couple of ways. First of all, if you also additionally had a Hermitian form, for instance, if you were already valued in Hilbert spaces, then a symmetric form plus a Hermitian form, there's symmetric form, Hermitian form, and their product is a real form, a real structure. Or the ratio of a symmetric form and Hermitian form should be a real structure. So these are not that different. Although I agree, a symmetric form seems quite foreign from the perspective of doing Hilbert space theory. Real Hilbert spaces are not that foreign.
Oh, that's right. That's what one expects for the unoriented theory. Yeah.
That's right. So, I would say that. I would also say I didn't actually tell you how to give the Bordism category. I just sort of told you, because I was running out of time, I just sort of announced we know how to give Bordism categories, these Dagger structures. At least for the stable case. And what the Dagger structure does is that it also can rotate, it can reach in and change around the H structure. So for instance, you could ask, what is the dual to amorphism? So you can do this already just in one dimension. you could ask, here's a sort of easier version, which is rigorous. It's not contingent on this conjecture I made about PLN actions. So here's a sort of easier version of what I just of the theorem about fully extended things, which is a non-extended version. So you could take the category of board kind of and just the one category, the infinity one category. And now it doesn't matter if H is smoothly stable or PL stable. Okay, smoothly stable or PL stable. Doesn't matter. If you don't care about the difference between smooth and PL anyway, then you can ignore that comment. So let me tell you the dagger structure on this. So this, I forget who this is due to. Probably Lucas. Lucas, what I'm about to announce. It's probably something like Mueller, Stehauer.
Yeah, I think you should probably put like Craig, Teichner, Stolz, unpublished somewhere. Yeah.
Stolz. And did we decide if this is actually the same as Freyd Hopkins as well, or no? Should I put their name on this too?
Yes, it's the same. You should also put Freyd Hopkins.
Okay. So let me tell you a dagger structure on the unextended Bordism category that was done by those groups. So I claim that this is dagger. So what I'll actually do is I'll actually give it a flag dagger category structure. And then you can univalent size to being a dagger structure. So the flagging will be that I take, okay, I have to give it a whippage structure. So the whippage structure is the following. So let's see if I can remember how to do this. So I need to give you sort of an anti-involution. I need to tell you for every morphism what a dual morphism will be. Well, this is, so let me point out the following. So first observation is that there is a canonical anti-involution because I have duals. So I could take every manifold to its dual object and every morphism to its dual morphism. So this is a fixed point structure, a whippage structure. So it is a fixed point so it identifies C with its opposite in a symmetric, in a Z2E way, a symmetric way. But it's not the one I want, because you typically cannot trivialize this on objects. So for instance, this whippage structure, if you have an orientation around, this is the thing that takes a manifold to its orientation. It certainly reverses orientations. And not every manifold is isomorphic to its orientation reversal, if you have orientations there. But that means other whippage structures, using this one, you can take any two whippage structures, and whippage structures are a torsor for actions. So any other whippage structure will be this up to an automorphism. So to give another whippage, I need to give, it suffices to give a Z2 action on board and H. And that's the one I'm actually going to do. So because H was, let's see if I can remember how, see if I remember how to do this. So an H structure on a manifold, I took the manifold to BON, and then an H structure of the stable thing. So an H structure was a lift through BH. This was my H structure. And I can get another H structure by how do I do this? There's a sort of, yeah, so basically what you do is you look in this sort of in the stable directions and you rotate those around. So, so this is the sort of standard embedding, and you have a kind of negative of the standard embedding. So you take M with H structure to, so you take the negative of the H structure. Okay, I'm forgetting how to do this. So I need to give, so the H structure was a lift together with a null homotopy here. So what I'll do is here's the standard embedding. I take another copy of the standard embedding, but I use the -1 map. That sort of, there's an interesting null homotopy that uses the fact that BO is a group. So because BO is a group, you can sort of, there's an interesting automorphism of the standard embedding called -1. And so this composition, so this diagram is another H structure. So what this did was it reached in and sort of changed every single stable direction. The way you should think of this is the following. So what I'm really doing, I have my H structure, stable framing or whatever. I'm looking at the tangent bundle plus R infinity, and I'm giving an H structure. My input is an H structure on the tangent bundle plus R infinity. I can get a new H structure that reflects every direction in that R infinity. And then you can figure out that if you look, so that's the Whippage structure. And if you look at an n-1 manifold, then the tangent bundle to that so that would have a map. There's a sort of tangent bundle map to BO n-1. But I'm really using just the n-dimensional thing. So I get an extra O1 here. There's an extra O1. And you use that to untwist. I'm saying this completely badly, I'm sorry. I should not have tried to say this without corrupting it. The point that I'm trying to say is that what the Whippage structure does, and then the trivialization, is that the Whippage structure reverses the H structure. So the Whippage structure on a morphism, the Whippage structure does two things. It reverses the direction of time. So that was just using the fact that I had duality to reverse the direction of time. And it also reverses the H structure. So if H was just an orientation, it would also take the opposite orientation. And then on just a single manifold, if you just, so this was on an n manifold. And if you have an n-1 manifold, an object in my category, if you reverse the direction of time, but also reverse the H structure, those two can be rotated back into each other. Because you're because now the time direction is a sort of stable direction. So it can rotate through the other stable directions. So anyway, the point is that this sort of does involve a lot of orientation reversing operations. And so the reason I brought this up was to say in your question about like, what is unoriented Bordism, how does that play, is that unorientation is prevalent in this construction. And, but we haven't done a full investigation. Like I gave a definition, I sort of said, here's a tentative definition. We have not yet, and I don't think I will be part of this, so my co-authors have not yet worked out say what the full, like what a cobordism hypothesis should say, and whether there is a good cobordism hypothesis for this notion of unitary CQFT. I think I could imagine refining this definition. Well, the refinement would be that I haven't told you what the right definition of symmetric modal Dagger category with adjoints is. So probably, I think this definition, the way I said it, is correct, subject to deciding precisely what symmetric modal Dagger category with adjoints should mean, and how much the symmetric modal structure should kind of permeate the rest of the words. And so that'll be driven by examples and by kind of having a good cobordism hypothesis.
Excellent. Any other questions? Theo, if not, let's thank you again for being.
Thanks.